For some reason, the recording for part two was not recorded, so I regret that while I was recording, the voice wasn't recorded, so I'm re-recording a little bit. But the slides are written already, just because I wasn't sure. I wasn't aware that it was not recording. So in 18.4, we discussed the resistivity. The resistance of a wire is actually directly proportional to length, and it's also inversely proportional to area of cross section. If the area of cross section is wider, then the resistance will be lesser. But if the length of the wire is long, the resistance will increase. So when we combine these two laws, this was an experimental work that was done, and they found out that resistance has a constant. It depends on the constant, which is dependent on the nature of the material, and that term we call as resistivity. So resistivity is then dependent on the area of cross section also. So this formula can be used to find resistivity as well. So resistivity can be written as resistance multiplied by area over the L. So you can use this formula to find various things. You can find the area of cross section, you can find the length as well. So this is the table that gives you the values for different materials. We can see the conductors over here and the semiconductors in this region and insulators. So you can see how the resistivity is increasing down the table, and of course the resistivity will increase with temperature, while as resistance decreases with increase in temperature. So this was one of the examples that I was discussing when it was not recording. So if we have a car headlight filament, it's made up of tungsten and has a cold resistance of 0.350 ohms. So if the filament is a cylinder which is 4 centimeters long, we have to find the diameter. So we have been given resistance, as you can see, and the area of the conductor. Because it's a cylinder, so we know we can use the area as the area of cross section, which is pi r square. But since we are looking for diameter, r is d by 2, so r square can become d square by 4. So once we find the area using the resistivity formula, we can go ahead and find out the diameter. So here I have used this equation to find the area by substituting the value of resistivity, which I obtained from the table. Since the material in question was tungsten, I took the value from there. Okay, so 5.6 cross 10 raised per minus 8 ohm meter. The unit of resistivity is ohm meter, and that's the length and divided by the resistance. So I ended up getting the area of cross section as 6.40 cross 10 raised per minus 9 meters square, and then I equate this with that one and get the diameter of the tungsten wire or the tungsten filament that's used in the car headlight. So we end up getting 9.0 cross 10 raised per minus 5 meter. In the same way, the next slide talks about the temperature dependence on resistances and the resistivity. These familiar thermometers that you use at home are basically thermistors, and they are dependent on the temperature. The modified temperature, modified resistivity is dependent on the initial resistivity plus the initial resistivity and coefficient of resistivity multiplied by delta T. We are not working on no problems from this part, no problem solving. From this formula, but you should only conceptually know that resistivity and resistance has a relationship to temperature. So then I went ahead and was trying to solve the one of the textbook problems, which says what is the diameter of 1 meter length of tungsten wire whose resistance is 0.32 ohms. So again, you use the equation R is equivalent to rho LA, and basically you find area. Once you find area, the area of a cylindrical wire will be pi r square, which is pi times d square over 4. Just follow these steps, go ahead and substitute the values and get the diameter. It's pretty simple, like the example that we did just now. And in the next problem from the textbook, you go ahead and follow the steps, try to understand the problem and check the solution as well. You have to calculate the ratio of resistance of a 10 meter aluminum wire, which is 2.2 millimeters in diameter, so diameter is given, and 24 meter of copper wire, which is 1.8 millimeters in diameter. I've given you the resistivity of aluminum and copper. They are good conductors. So you find the formula for resistivity for Al and for copper is given here. I'm just substituting the subscripts Al and Cu for their respective metals. So you can see this is the length of the Al, this is the area of the aluminum, and then you go ahead and divide to find the ratio. So the following steps are mathematical, which you should be able to work on. The 4 and 4 and the pi's and pi's cancel out, just like you can see. And then you go ahead and substitute the values that are given to get the ratio between the R aluminum and R of copper, which comes out to be 0.44. So the next step was to find the electrical power. The electrical power is basically the energy transformed per unit time. In chapter 17, we learned that electrical energy is related to charge multiplied by electrical potential difference delta V, which in this chapter onwards, we write delta V as simply V. So the electrical energy is Q into V, where V stands for potential difference. And so power is basically energy transformed per unit time. And if you look at this Q over T, there is a term, this is the current. Charge per unit time is current, and that's why power can finally be written as I cross V. If you use the formula Q by V, Q by T for I, and V was from the formula that we have Q multiplied by V is equivalent to delta U. So with the help of Ohm's law, we learned that I is equivalent to V over R. These are the different ways to write it, by multiplying or cross multiplying differently. So if I write V, this is V is equivalent to I, R written in different forms. So from one equation, we can have 3 different configurations. And if I substitute this, if I substitute first for V, it becomes I square R. If I substitute for I as V by R, then it becomes V square over R. So we can write power in 3 different forms. P is I cross V, P is I square R, or P is also V square over R. And the units that the power has is the SI unit is watt. 1 watt is actually 1 joule over 1 second, because power is energy over time is power. So joule over second is 1 watt. So the units can be 1 watt, it can be kilowatt, which is a bigger unit, it can be megawatt, which is 10 raised power 6 watt, it can be gigawatts, which is 10 raised power 9 watts, and so on. So then there was an interesting example of power that a lightning bolt can generate. So if you have the energy produced by the lightning bolt, if you assume it is 10 raised power 9 joules, which is a typical energy. And if the voltage between the clouds and the ground is, there's a potential difference. If the cloud is positive and the ground is negative, there's an electric field that is created, and that there's a potential difference also created, which is of the order of 5 cross 10 raised per 7 volts. If the lightning strikes for 0.2 seconds, then I can find different things. I can find out first how much charge does this lightning bolt hold. I know that electrical energy has a relationship with charge and voltage, which is potential difference, also known as QV. So you can go ahead and substitute the values or rearrange these terms. Q will be delta U or delta V. So it gives me 20 coulombs of charge that is produced during the lightning bolt, which is a huge amount of charge. And I can also find out the amount of current. If I know the amount of charge produced and I know the time during which the lightning bolt was striking, I can find the current. So it seems like the typical lightning bolt can generate about 100 amps of current. It's a tremendously high electrical current. Then we know that the power is electrical energy over time. So the electrical energy is 10 raised per 9 joules divided by time is 0.2 seconds. Once you work on it, you get 5 cross 10 raised per 9 watts, which is giga. Giga means 10 raised per 9. 10 raised per 6 is mega. 10 raised per 3 is kilo. And so on. Again, the electrical power can also be represented in kilowatts, in megawatts, just as you saw. But then there is one more unit for electrical power, electrical energy, the one that you get the bill for. Electrical costs or electrical bills are generally given in the form of kilowatt hours. Where kilowatt hour is nothing but unit of energy. If power is energy by time, energy must be power multiplied by time. So if power is 1000 watts, which is kilowatt, and time is 1 hour, so 1 kilowatt hour is 3.60 cross 10 raised per 6 joules. So that becomes the 3.6. 1 kilowatt hour has 3.6 cross 10 raised per 6 joules of energy stored in it. Based on this, you can also go ahead and solve the problems based on power. The maximum power consumption of a 3 volt CD player, which draws a current of 240 milliamps. Remember, milli is 10 raised per minus 3. Milli is not mega. Mega is always used as capital M, and giga is always used as capital G. So you can solve this as a simple problem. Go ahead and substitute the values. And in the same way, we can you can look into the problem number 31. There's an electrical car that is a battery of 16 kilowatt of energy, and you have to find how many coulombs of charge would need to leave the battery. So basically, we are again using chapter 17 formula between delta U, Q, and delta V, where, as we just mentioned, that delta V can simply be written as V. So go ahead and substitute the values and rearrange on the terms. If all the units are in SI system, you know that you can simply write coulombs for your charge. The amount of charge that is leaving the battery and entering back into the 0 volt terminal is 1.7 cross 10 raised per 5 coulombs. So then there was this problem that we worked on to find out how much cost does an electrical toaster, how much it costs to operate an electrical toaster 5 minutes every day if the toaster has a wattage of 550. What if 9 cents is the cost of the electrical energy per kilowatt hour? So you find out how much money you are spending every month on that. So if you look and follow the steps, the electrical energy is 550 watts, power multiplied by time. So if you look at, this is the power, and we are converting it into kilowatts. So then this is the time, 5-minute time. So hour, minute, and minute goes away. So the energy consumed each day to use this toaster for 5 minutes is given by this. So what would be the cost if per day is this much energy? What will it cost to use 4 days per week? And 4 weeks, if we assume that there are 4 weeks in a month, then how much will be the cost per month to use toaster for 5 minutes per week? Or so it will, if the cost is 9 cents. So this is just a unit unit and dimension solving problem. So the cost comes out to be 6.6 cents per month.